Good afternoon, everyone. So I'd like to start by introducing myself. My name is Biglari, and I'm a student at the University of California, San Diego. This summer, I had the chance to conduct research here in Boston College with Dr. Kenneth Birch and Mason Gray. And the title to my talk is the optimization of graphene-based biosensors fabrication. So this is basically a continuation of my peer here, Dennis's talk, and I'm working on the physics part. So as an outline, I'm going to talk to you about the antibiotic-resistant bacteria, and I'm going to, as a problem, and then I'm going to propose the solution to it, and then the graphene and fabrication of biosensors, and I'm going to share with you some of our results. So antibiotic-resistant bacteria. So there are bacteria, and sometimes these bacteria are good, and to some, I would like to say, I mean, they're sometimes essential for life. However, they become a problem when they build a resistance to antibiotics, and mostly antibiotics are used for basically getting rid of the bacteria in the case of illnesses and diseases. So this happens when a colony of bacteria caused a certain or a particular illness, and you want to get rid of them. These bacteria have, basically they can adapt to the environment in which they are in, and if you do not use if you don't identify them correctly and you don't take the right antibiotics, they can build resistance. So as you see in the number 1 here, we have a colony of bacteria due to mutations or whatever else, what else it could, I mean, whatever it could cause it. 2 of them have survived, and those 2 not only have survived but thrived and built their own colony of antibiotic-resistant bacteria. So current technology in bacteria-resistant bacteria, in antibiotic-resistant bacteria detection. So the current technology is mostly, I put over there limited current technology, time-consuming and expensive, and also inaccessible. But the current technology is basically based on doing the lysis on the bacteria, which is like basically just ripping the particular bacteria's stomach open and then separating the DNA, the RNA, and everything else in there, and then identifying the particular part of the DNA that you want, and then basically just going with that and detecting it and identifying the bacteria. Now this is the problem because it takes so long to identify that particular bacteria that physicians really can't treat an illness in time. Sometimes patients have to die or have to wait longer than expected or get treated with the wrong antibiotics within the period of time that they're waiting for the identification of the bacteria. And since we live in the 21st century, we would like to have a device or some sort of a technology that can identify the bacteria rather quickly and easily accessible, and basically like a drop of blood or urine, and get the results texted to your phone perhaps. So graphene and sensing. So graphene, I'm going to introduce graphene and talk about it a little bit. So graphene is a monolayer of carbon atoms tightly bonded in a hexagonal shape. Graphene has a property which is like, it is very sensitive to charge, and that's what makes it very important in our studies. That's not the only property it has. It is strong. Its bonds are strong, and that's due to the carbon bonds. And to the point that Samsung has patented a cell phone that can be bent, or car companies are looking into building cars that can turn the sun energy into electrical energy for the cars to go further than ever before. So there are some, in electricity and magnetism, I would say, class, there are some rules and laws, Ohm law. I don't know if I have. So if there is, actually I'm just not going to get into this, but there is, does anybody know how to use the light on this? The top one. Okay, so previous studies have been done in University of Pennsylvania by Charlie Johnson and his group, and they have done this experiment like 20 to 30 times, and they have the minimum of their graph of current versus gate voltage, and each time the minimum of their graphs, of their peaks and graphs have been at the same spot, showing that their systems have followed the same pattern. And as Dennis was talking about it, as they added any molecule, like their P-based linker, or their probe DNA, or their target DNA, the minimum of the graphs has moved. Now, this has been studied and it's been proven before, but we are trying to make it, basically make improvements to their studies. Improvements such as a 4-probe measurement, which can directly help us with to get a resistance measurement directly. And we have a microfluidics, which can increase the chances of sample coming in contact with the graphene, which is going to be right between the contacts here. Also, we are using glove boxes, as you saw in Ryan's presentation, which is a very totally inert and clean environment to decrease the chances of basically systematic error in the future. So like every other project, science project and research, which they have different components and different parts to it, ours was no exception. I personally was working on photolithography this summer. Photolithography is used in micro and nanotechnology and fabrication, and basically it is a layer of photosensitive material is laid on top of a substrate, and then you expose that photosensitive material to light of a particular wavelength, UV or whatever, and it becomes soluble. Then this soluble photoresist, you can introduce it to developers, and it develops. And as you see, we made this one here, Hello Boston College, in the lab the other day. But usually, this is how it works. So there is a substrate, silicon dioxide on silicon, and with a layer of graphene on it. Then we have bilayer resist on top of it, which is one layer of it is LOR, lift-off resist, and the top one is S1805. S1805 is the photoresist that I was talking about, which is becomes soluble, and LOR, the purpose of it is to help with the removal of the layer of metal contacts, which I will talk about it later. So we introduce this to light, and we get a particular design on top of it. We introduce that to developer, and the soluble part, which was exposed to light, becomes, it is removed. Then we deposit metal contacts in the position machine. We have angstrom in the lab. In our case, we did chromium and gold. Now, these areas here are the part that the LOR helps us remove them easier. And this will become our final design. Now, in the process of laying the LOR and the S1805, each time we had to bake them, and basically we baked the LOR at 175 degrees Celsius for 5 minutes, and then we had to wait for it, and the S1805 for 1 minute at 105. So, we had previous attempts. Well, this past 10 weeks I have been working on improving this system, this device on this substrate here. So in the beginnings, we really did not have the correct parameters to make these work. And we had to, basically on daily work, we had to change these parameters one at a time, like any other science thing that you do, and you have to change one parameter at a time so you can understand which one was the cause of the improvements. So we had to change the parameters. For instance, the developer, we had to dilute it from 1:1 to 10:1 dilution factors with DI water. And or the laser power, we had to increase it from 4 milliwatt 50% to 6 and 8 gradually to 8 milliwatt 60%. And or the timing of the substrate in the dilution, in the diluted developer. We went from 30 seconds to 5 minutes. And we found out that our best parameters used were actually 8 milliwatt laser power and 10:1 dilution factor for the developer, as well as 5 minutes time spent in the developer. So this is the beginning attempts that, in the beginning when we started doing this project, these are the attempts. And as you see, they weren't that good, but they were, as we changed the parameters, they got better and better and better. And at some point, we got improved devices, which are very well defined and perfectly shaped devices. I have a few here. Okay, and this is one of our finished devices, which is, by the way, week 8 that I finally was able to have one device. And so as you see, the graphene is where it should be, as I talked about it earlier, and the metal contacts are there. And to make sure that what we see is what we have is, and what we see is exactly what we want, we did Raman spectroscopy, and we measured our graphene in 3 different sections of the device. So in the edge here, okay, I need to first tell you about some of about the graphene peaks. So graphene, when you put it in the Raman spectroscopy, it gives you two distinct peaks. One at approximately 1650 nanometer, and the other at 27, I believe, 2750 and 1600. So the one in the edge, where we didn't want it to have graphene, as you see, we have very little on the 1600 one, but have none at the 2700. And the one in the middle, which we wanted it to have graphene, as you see, has 2 very distinct peaks for both areas on the graph. As well as further down in the line, we do not see any graphene peaks in the 2700 and one, I think very little one here. So in conclusion, again, I talked to you about antibiotic-resistant bacteria. I proposed a solution to it, graphene and fabrication biosensor, and results. Next, I think our lab is going to proceed with reproducibility of this, making devices more and more. And also, I think the goal is to have more, basically places, more graphene spots for different linkers to attach to it for identifying more bacteria on one substrate instead of having to, yeah. At this point, I would like to extend a warm thank you to Professor Kenneth Burch for all of his guidance, Mason Gray, and Leslie Schmid, my peers, and hopefully future colleagues that are in this program with me. You guys put up with me for 10 weeks. I don't think I would like to do that myself. And Boston College for hosting us, as well as National Science Foundation for funding us. Thank you.
Questions?
So I just want to clarify, what you're working on is the site that the linkers would connect to?
The site that the linker would connect to, no. That's where the graphene should be, but I was working on the project as a whole.
Okay.
Yeah, that's the ultimate goal. Like, we really want that graphene to be where it should be.
I see.
Laura?
Yeah, so the device that you were making where you put in the graphene, I noticed, and I don't really know what I'm looking at here, but there's these 3 lanes, it looks like, is that correct? Like there's 3 spots, right?
Are you talking about the laser spots?
There's, yeah, they're right there, but then there's these 2 other side branch things, right? And they're thinner. Like, what's the significance of having those 3? Do you know what I'm talking about?
Oh, it's gonna come up now. Which 3?
There's like 3 lanes, that's what I see. And
Okay, here?
there's the center one where the laser spot is, and then there's just 2 side things.
Okay, yes. That's actually supposed to be 4, which you see, I don't think there's any significance to this 3 as much as the significance is here because as the graphene goes there. So there is no 6,
Okay, so there's 4 that, okay, so the graphene.
those are the contacts areas,
Okay.
yes.
So what's the significance of the different shapes? That's my
They're not
question.
different, like the shapes here and here.
Yeah.
I think it's just the design, the plain design. I don't think there is any significance to it.
But why design it that way? For fun?
I believe so.
So this is microfluidics you are going to use it. Is it similar to flow cytometry? Then that can be explained.
What is it?
So you said that you're going to use microfluidics.
Yes.
So in the fluid, so in a normal in cell culture, in the scientist is flow cytometry, okay, using the mechanism. So in this case, 2 different layers can be explained. Why we have 3 layers over there? Maybe that has tunneling effect to moving and converging.
I think, if I understand your question, is like the purpose of the
Yes. why we have-
microfluidic?
Yes. Lorraine asked why we have 3. Yeah.
So there's no fluidic there yet. It's
Okay.
just that what you see are the 4 gold contacts.
Okay.
So the purpose is that you can put current through 2 of them, the ones on the outside, and measure the voltage drop on the ones on the inside. So the main reason for that is in the previous studies, people only did 2, so you never know exactly what the contact is doing from the graphene. So when you have 4, you can separate out your contact from the graphene, but it means that the fabrication is much harder, hence her work to get it right.
You seem to have a lot of questions today. Maybe you would have sat here in the front. That would have been a little bit better because it's really hard to hear. But
There's a question.
yeah,
So earlier in the slides, you talked about how you removed part of it and you had 2 like metal layers, and then you removed the other parts or whatever. Is that like what this is?
yeah. The metal contacts that you're talking about, this.
Yes.
So basically, this is just to represent. It's just like to make an animation of that. But
Oh,
this
okay.
is supposed to show what you saw there.
So
Yeah.
those 2 yellow beams are the metals, right?
Yes.
Okay.
It's one layer of chromium and gold
Got it,
on top
okay.
of it. Yeah.
Any other questions? Okay, let's thank our speaker and all our speakers.